Yeah, hello everyone. Today we are building this kind of mycelium growing solver or roots growing solver, whatever you want to call it. First we dive into some explanations how the algorithm actually works, and in the second part I show you my final capsule. So we build kind of a simple version, and then my final capsule will be a bit more advanced. So before we dive into the explanations, I get a lot of questions about if I can do some beginner tutorials. So for this, I actually can recommend the new tutorial series of Core4D. They start from the basics and go up. I think they're around now, like they have 12 tutorials, so where they start from super beginner level explaining all the nodes. So if you are a beginner and want to dive into nodes, I can recommend to go to Core4D and check out their tutorials. Okay, before we start with the simple setup, here are some explanations first how this works. So what we need first here is a bunch of points, and then we iterate over every point here, for example this one, and search for the closest neighbors. And then out of the direction from the point to the neighbors, we're building an average direction, here showed in blue. And then we add this average direction to the point position and we get a new point, and then we connect those 2 points with a line, and that's actually it for the algorithm. So but what we need too is a condition. So for example here for this point here in the center, when we collect the neighbor points and we build an average direction out of the directions to the neighbor points, we get a very short direction. So that's something we don't want. So we say if it is too short, then we don't create a point and a line. And then when we do this over and over again inside of a memory solver, we get this kind of look here. Okay, that's it for the explanation. Let's jump into Cinema. Okay, here inside Cinema, what we need first is a nodes capsule. So we search for group, and then we use the object group capsule. I can recommend when you build and set up, start with the object group capsule, because this one is actually good for debugging and visualizing stuff. And at the end, we will convert this to a spline capsule because we are building splines. So, okay, then let's jump inside nodes. Maybe this here and this one here. Okay, what we need first is some points. So let's make a disk first. Then we scatter some points. We can use, it is called surface blue noise distribution. Then if we like to see the points, let's make maybe a cube to visualize them. Make this small, 2 by 2 by 2. Then toggle the node type, so we have an actual operator here. Then we put the distribution here into the matrix. Then it iterates over the distribution, and then we can plug this here to the output. Then let's zoom in, and now here we see we have our points. At the moment we have 100 points. That's fine for the moment. Maybe already promote here and make a parameter here. And when you look inside the distribution here, we have here a lot of stuff, the matrix, the index, all the stuff we don't need. We actually just need the position. So prepare this first. We like to collect just a position inside a new array. So let's assemble a collection. Assemble collection. Then we like to have vectors, and the vectors are inside of an array. So then connect this here to this, and now we have here an array with vectors with our positions here. Now we like to iterate over the points here and search the closest neighbor point, so the closest points to for each point. So we use an iterate collection. Then we use our good old friend, the closest points. So the geometry is actually here our points array, and the query position is each individual point. And then here on the closest point, we also can decide how much neighbors. So maybe start with 20. Also promote this parameter here, make an input out of it. And then we iterate over the nearest indices. So another iterate collection. And then we have here the indices from the closest points. And then we use a get element to get here the point position of the closest points. And now we like to build the direction, like here, all the directions. So we can use the initial position and subtract the initial. We have first to switch here to vectors. Then we subtract the neighbor position here from the initial position. And then we like to normalize this direction here. So normalize means that every vector has the length of 1, and then we like to collect all, like here, collect all those directions inside of an array. So a sample collection, then also vectors inside an array, then close here the iteration and feed in our directions here into the assembly collection. Then we like to have here this average direction. So we can use an arithmetic for this. Here array arithmetic, then switch it to vectors, and the operation is already average. That's fine. So and now we have here the average direction for every point. And now let's visualize those directions. So we can do this with an assembly spline. Assembly spline here, switch it to linear. So and now we need an array of points. So we add the direction to our initial position here. Add vectors. So first we add, we need also an build array first. Build an array. Also with vectors, we just need 2 positions. So the initial point position, and then to the initial point position, we add the direction, and then this inside the build array, and then this into the assembly spline. And now let's use a child operator first, so we can connect here our cubes together with our lines here. So add this in here, and this to here, and then back to here. I made a mistake here. The iteration that we have to close here is not the iteration over all the points. It's actually the iteration here over our neighbors. Then disconnect this one, and here we go. And now I think we don't see them because they are very small, so we can scale it here. Scale our direction here, switch it to vectors, and now here you can see our directions for each point. And as I explained here in the second part, we have here in the center, we have pretty small directions, so we don't want those. So what we have to do here is to check the length here of our direction here, of our vector. So vector length, that is in here. And then we have to compare here the result. Compare. And then we ask, is the length greater than a value? So we can add this also as an input, say min length, for example. Then say, okay, the minimum length is maybe 10. So now we have here in the build array, have kind of our segments here. When you say those lines, those 2 points here. So we first collect those inside an array. So we use an append element. Let's say these are our segments, and the segments are vectors inside an array, and then again inside an array. So we have here an array with an array inside. This is actually here our individual segments. So we add this to here, and now we can decide here with the count if we like to add a segment or not. So we can use here our result of the compare. So let's add this here to our count, and then plug here our segments back to the assembly spline. And now you can see it deletes the small direction. We just have the long directions here. And now, because we like to have this step on each frame, we have to collect, we have to put our setup here inside of a memory node. But first we have to decide what we like to update on each frame. What we like to update here is our segments here. So because we get on each frame we get more segments, and of course we have to collect our new points. So let's also say append element and say here points or positions or whatever, and these are vectors inside of an array, and also the count here, and then here our new point position. So the point position is the initial point plus the our new direction here. So we add this here to the new points array here, and then we have to collect everything inside of an memory solver. So we don't need the cubes here anymore. Let's hide those. And here is our point array. That's what we like to update. And here is the end of here's our new point array. So we collect this stuff here. And then we go to create and then group nodes as a memory And now we have everything inside a memory solver here. But we have to make some adjustments first. So as initial values, we like to have the first one here are our positions, because we like to update them, and those positions are inside an array. So we can plug here our initial points to here. And what we need also is our segments. So our segments are also vectors inside an array. Also inside an array, and then let's call them segments. So they are at the first frame, they are empty. It is empty here. So then go dive into the memory solver and then connect here this one, maybe connect them first here. So, and then we like to connect them with the positions. And this one too here. So we like to append to our initial position array, and then this goes here to the output, and the same for the segments. This to here, this to here. We don't need this anymore, and also this input here. Okay, let's jump outside of the memory and bring this stuff together here. And then here our segments, on that we can choose the previous or the next. Let's choose the next here, and now we have here on the first frame also our first segments here. And now let's press play and check, and you already see something has happened, and we already got here our mycelium look. So when we play it here, let's go further, we see, okay, it looks very regular, so maybe it's a good idea to add some noise to our direction to get a bit more interesting look. Okay, jump back into our memory solver, and then here is our average direction. So we like to add some randomness in between here. Maybe, and it's also good here for the scaling of our vector. Maybe let's make also an input here and parameter out of that. Okay, then we use an hash node. First, we like to decide how much randomness. So maybe it's also good to have here a parameter for the minimum and the maximum. So let's say the maximum here as a parameter. Then say, okay, maybe 0.5. And then the minimum, because we want to go in every direction, let's negate the minimum. For the minimum, let's negate it. Oops. So here, negate our input here. So we have minus 0.5 and put this into the minimum, because we like to have randomness for each point. Let's add here the index to the seed, and maybe we also like some randomness for each frame. So let's use a time node. And then the frame, maybe we can put it into the salt, but we also can add our own seed first. So use an add node, switch it to integers. So add the frame, and this here is our, let's call it random seed. Also maybe here random amount. this here to the salt. Then let's go back to 0. And then we have here random vector we like to add to our direction here. We use an add. And because we like to have it in 2D, we just add the X and C value here. We also can add every component here, but then it gets kind of, the mycelium goes also into 3D. We can try this at the end. So let's use the direction, then add X and C, and then this back to the scale. And you already see we got here some randomness. Okay, let's check. I think this is way too chaotic. I think that's way too much randomness. So let's go slow on that, maybe 0.1. Let's check again. Yeah, maybe a bit more, 0.3 or 0.22. Then let's play. Yeah, and you can see we get some randomness. It's not too even anymore. Okay, then let's build here our parameters here. Here's also, let's call them here minimum length. And this one here is our scale. So direction scale. Let's go out of the memory node and then also add here the direction scale, here the random amount and the random seed. And we have here our parameters. So let's go to edit resources and let's organize here a bit. So first we like to have here our count here. Maybe say default is 100, step is 1, that's fine. Then here our maximum neighbors, maybe say 20, step is also 1, then minimum length, maybe 10, step maybe 0.1, then the direction scale, maybe say 20, step also 0.1, random amount maybe 0.2, step 0.01, and the random seed, put in a seed value, and step is 1. Okay, and now we have here our parameters, so let's play around with them. So let's go to the standard layout. Let's check. So, okay, for the moment it looks like this. So, and when you go lower here, for example, with the neighbors, you can see you get different results. It blows up here in the center. So I think we have to reduce the randomness. And also reduce maybe the up the minimum length. Oops, that's too much. Like this. Let's try maybe here direction scale to 10 and the minimum length to 6. Maybe some more neighbors here. Let's check. Yes, and then some randomness again, maybe 0.4. Let's try this. Yeah. You can see you can play around here with those values, so you get different results. Maybe a bit less randomness. Yeah. So yeah, let's play around with the values and you get different results. You can see it gets slow pretty fast, so we can optimize this a bit. Maybe let's first show the frame. Oops, just show the frame rate here. Activate the frame rate. Maybe you can see here around frame 50. We're around like 3.3 frames per second. So that's because here when we convert here our capsule here, you can see we have a lot of splines, so we can connect all those splines. So then let's dive back into our capsule. So what we can do now, because we iterate here over our segments, let's iterate also over our points and fill all our points inside of a single array, and then add those points here into our assembly spline. But we also have to decide the segments here. So let's use an iterate collection. Add this to here. Then we need an append element. So we like to append vector inside of an array. So add this to here. And then because we're iterating here over our segments and over the points of our segments, you can add both curly brackets here to our append element. It appends every point into our array here. And then we also have to define here our segments. So we also use an append node. Oops, so, and here inside our array here, there are integers. So replace it here. And now, whoops, because every segment has 2 points, say, okay, the value is 2. And then for every segment also plug in the curly bracket here to this curly bracket. So it appends for every segment, it appends here the value 2. Before we switch those two arrays here, we switch here also the segment to the previous. So we have here an empty canvas on the first frame. Then add this to here and this to here. And then let's press play. And you already see here, we are much faster. So let's go back to the standard layout. And now let's watch the frame rate here. And you can see already it is much faster. Maybe up to add some frames. Oh, yeah. You can see here we're around like 4 frames here on frame 150. Yeah, you can see the difference. It is a much faster setup. For the last step, let me show you what will happen when we add noise to all directions. At the moment, we have just noise in two-dimensional direction, so it is flat. So let's open our capsule, go into the memory solver, and also add here the Y value, and you will see what will happen. Let's press play. And now you can see it goes in every direction. Yeah, if you like to have this kind of look. Maybe add this to an sweep so we can see it better. get something like this. Now for the final step, as I said at the start, let's make a final spline capsule. So maybe deactivate the sweep. Let's go back. Then let's open here our capsule. And then we can go to create, then change group type and say we like to have a node spline. So now you can see it switches to a node spline capsule. And then because the output has to be geometry, we don't have to build here an actual operator. So we can plug in the assembly spline straight to the geometry here. Let's close it. Let's press play. And you can see we have the same result, but now we have an actual spline. So you also can sweep this. Yeah. I think that's it for this part. And now let me show you the advanced capsule. Okay, here inside our advanced setup, here you have our capsule. So when we have a look at the parameters here, first we can decide a source object here. It's this sphere for the moment. And of course you can decide a polygon selection where the growing has to start. So these are these polygons here. Let's press play and you can see they start to grow on the surface. You have here a project to surface checkbox. So when you deactivate this, it starts to grow in all directions here. Let's check this again. And then here you have the start points. Of course, you can go higher. And then you have more of those tendrils. And then here are some settings for the minimum, for the speed minimum and the speed clamp, so that decides how fast they can grow. So when we go low here, maybe say here 2, you can see it is much slower. You can go pretty high, maybe 10. Then you see it starts to grow much faster. You have those longer tendrils. Then set this back here to maybe 5. Then you have here a grow probability. So when you go super low here, you can see you get less tendrils, so it grows much slower. Or you can go straight up to 100%. So it grows on every point on every frame. So this also speeds up the growing effect. Then you have here a grow seed. So the seed is working together with the probability. So when you go lower here, and then there is here also a maximum age. That means that when a point is older than 40 frames, it stops generating those segments. So maybe when you go super low here, you can see it starts to die out pretty fast. So let's go back to 40 here. Then we have here a direction influence. So when we deactivate here the project to surface, we'll press play. You see it goes in every direction. So when we maybe up this here a bit, and then when we say okay, direction influence into Y plus, let's press play, and then you can see they start to grow upwards. And then here the random direction strength, that's what we also did in the simple version. So when we go here to 0, you have those more straight tendrils. Yeah, you can see you get a super straight look. Could also be interesting. And when you add a lot of randomness, maybe, yeah, get those super squirrely tendrils. And then, of course, you can randomize the direction here with this seed. So maybe go here back to 2. Then here are the neighbors to search. So when we go very low, you can see you get also a different look. So you have less branching here. Or you can go pretty high, maybe say 40. Let's press play. And then you get those tendrils with a lot of branching. And this here is the search distance. And then you have here the influence of the distance to each neighbors. So this also can change the look drastically. So when we go to 0, you can see it's maybe too much neighbor points. Maybe go back to 20. You can see you get a lot of tendrils. And when we go maybe here to 50 or 200, yeah, you get also a different look. This takes into account when it searches the neighbors, so the closest neighbors, they have a bigger weight onto the final direction than the neighbors that are far away. That's what this setting here, this parameter is doing. And now let's go here to the sweeping part. So we can sweep the splines here. So and when we sweep them, we also get here a vertex map. So let's play, and the vertex map is actually showing us the age of each segment. So red, these are younger segments, and blue, these are the older segments. So, and this is something we can use inside our volume measure here. So this, of course, here you can switch the radius. You can see it just builds those simple segments. So, but those segments we can use on the volume measure to color it. That's something that at the moment don't work on just splines. So when we have here just splines, we can't add a vertex map to the spline. So that's why I built here the sweeping. So let's activate this. And then here, of course, the radius, you can make them bigger. Maybe let's keep them at 1 centimeter. And then how they align. At the moment, they align in the Y direction, but we can project them onto the sphere. So now they are projected to the sphere here. And now it's the interesting part. Maybe let's grow it a bit. Let's add a volume builder and a volume measure. And now we get this mesh here. And you already see here on the volume measure, we have an vertex map, and the vertex map inside the fields of the vertex map, we have the age vertex map here from our capsule. And yeah, here you can see it, and this is colored with just a ramp here. You can see here we have the vertex map, and then we color it with the ramp. So then it looks, then it looks like this. And then of course we can make some interesting stuff with this. So we have here scale by age. Maybe let's deactivate this, go back here. And when we add the scale by age here, there was an update issue. I checked and unchecked and checked here the use deform points, but now you can see the All those individual polygon segments are scaled by the edge vertex map here, this one. So when we reactivate the volume build and volume measure, we have like smaller tendrils here at the tip, and here they are bigger. And of course, we also can use this for displacing by edge. Maybe go back here, activate this. And you can see we displace them outwards here, also depending on the edge here. So this looks like this. And when we reactivate here, we have also thicker tendrils here in the center, and then some smaller ones here at the tip. And the last step, add some smoothing here. Yeah, then you get a look like this. So yeah, these are all the parameters, and let's play around with them to get different results. And I think that's it for this tutorial. And of course, as always, you can download the files on Gumroad. And if you have any questions, let me know in the comments. And then I wish you a happy day, and we see us in the next tutorial. Bye bye.